Good afternoon. That presentation was a perfect setup because it points out all these complexities when you go look at an actual bridge system. And this idea of correlations from one bridge to the next is something you can only know by understanding your inventory better. In fact, one of the things we struggle with is when you have 100 columns versus one column in the bridge, should you make them more susceptible because there's more of them. So the project I talked about had really two parts. The first part I was leading was about characterizing the bridge inventory in the state of Washington. And so I've talked about that at the previous meetings. I don't want to come back and talk about that again. And the second part was, gosh, you have all these properties for about 800 bridges. Can we actually predict some of these properties? And we just actually took a leap of faith and said, well, there's not much information we have about any of these bridges. Can we use the National Bridge Inventory to at least reduce some of the uncertainty in predicting some of these properties? So this work was mainly funded by peer. Also got some funding from the Accelerated Bridge Construction University Transportation Center, and the Washington State Department of Transportation provided all these plans and all this technical support. So I want to acknowledge their contributions as well. And so today we're all talking about earthquake scenarios. And in the presentation earlier this morning, David was talking about how we have these great models. We can go down to resolutions of, almost millimeters, not quite, but going down to small distances. And now we're actually limited more by the knowledge of the actual Earth, not by the simulation results. And that was actually the whole goal of your project. I'd argue we had the same problem with bridges as well, which is that we're doing more and more and more work on getting better analytical models. We're doing better and better work on getting better fragility curves, but we still have a problem not knowing what the inventory actually looks like. And so if we have a detailed model of something which is uncertain, that's not an amazing improvement. And so we're taking a little first step on this and try to talk about what we might do. This is a picture of Western Washington State. Every red dot on there represents a bridge. So we're looking at just things west of the Cascades. If I look nationally, there's more than 600,000 bridges. In California, there's 26, and even in Little Washington State, we have 8,500 bridges. So what are we going to do when we do a regional analysis? We have ground motions at all these locations. Maybe with Brett's work, we have a better idea of what the site conditions might be. But all we have is National Bridge Inventory. And it's used all the time, because that's all we have. So every public agency, not the private ones, but every public agency is required to update this on a regular basis. And it has all kinds of information about identification, location, clearance, traffic inspection, funding owner. It's run from a management perspective. I want to know how many miles of highway you have, and how many bridges, and how old, and what condition they are, and how many cars drive on top of them. All those are amazing, but not, of course, what we want in seismic world. There is some structural information. Structure type. Is it a box structure? Is it a precast girder structure? Is it pre-stressed or not pre-stressed? Oh, awesome, that's great, but that's not really what I want to know. I can know if it's concrete or steel. That might help a little bit. A truss might be very different than a girder bridge. Maximum span length might give you a sense of what's going on. Deck width turns out to be important, at least in one way. And then certainly construction year, we know the codes have changed over time. And so what we're going to do today is talk about various ways we could get the information on the bridges. And what I mean by get, I mean guess, or try to get them at least better than a random guess. So first of all, we can certainly go in and load up all the drawings. So the state of Washington has, like most states, a database. You put in the bridge number and all that, and it comes up, and sometimes you have 2 pages because the bridge was built in 1926 and is fuzzy, and maybe throwing a machine learning tool at that drawing is not going to work so well. Or you have another bridge that has 250 pages because it was updated 3 times, and they added a railing, and they changed this, and they did a retrofit and all that, and it's pretty much impossible to digest without spending a lot of time. So you can do it, but it's very hard to do that for 600,000 bridges or even 8,000 bridges. And the other option is one that everyone uses, not because they want to do it, but that's all we have, right? Is that if you don't know what your bridge looks like, you're going to go and use the HAZIS properties, and HAZIS is intentionally focused on the properties which are in the NBI. So nothing wrong with that, it's just that's all that they have. And so what we found in doing a lot of detailed models of bridges is that some very key properties are in the bridge, but aren't in the NBI. And the clear one, certainly in Washington State, is we tend to use a lot of internal shear keys between our girders. It turns out those internal shear keys are almost indestructible. So we've done tens and thousands of, maybe hundreds of thousands of analyses. We have yet to break an internal shear key, which means that your abutment's holding onto the bridge. So that's a lot of bridges. Turns out in Washington State, that's about 70% of our bridges. They're tied at the abutment. So if you're trying to figure out what's going to go on, you sure the heck better know whether there's a shear key or not, or at least guess, right? Another option is rapid visual screening. ET Tasiroglu and others have done work on that. They use street view, they come through, they get geometries of bridges. That's extremely promising work, and we'll talk about that a little bit later. But of course, the challenge is you can't see in the bridge, you can't see how many longitudinal bars it has, and things like that. So, our plan and our walk of faith is to say, can I take the NBI information, which was really not related to bridges, seismic, can I extract some information from that to predict things we care about in the seismic world? And so the person who was going to give this presentation to begin with was Julia Lensing. She's actually a colonel in the U.S. Army, and she was told she has to move to Texas in the next few months, so she's busy selling her house. So I took the talk, and I decided I'm going to make it the bridge engineering version of using machine learning, which in a way might be helpful, because it kind of gives you a sense of things that I've gotten out of it without delving on whether XBoost or whatever is better than neural network or random forests or something like that. Okay, so the plan is pretty straightforward. It's like we always do in machine learning. There's national inventory, 8,000 bridges. We have a detailed bridge database where students spend hours and hours and hours collecting all the details that we might care about. We then train the algorithm for those 800 bridges. It's not a very big data set, right? 800 is very small in the machine learning world. I found it's actually one of the most interesting things is actually the feature importance, just to get a sense of what is actually tied to what. In some cases, it was obvious. In others, I said, oh, that's interesting. That gave me an insight I didn't have before. And of course, once you've trained your model, then you can go through and try to estimate the models. So whether using surrogate modeling or another technique, it's helpful to know more and more about that bridge. So the work we're doing is basically the front end, which would be able, at some point, to build a funnel information to say, well, your bridge inventory has a lot of characteristics, a lot of variations. Let's us try to narrow it down a little bit. Okay, and so just to look really quickly at the database, it's pretty common to bridges on the West Coast. Almost all, then we decided to focus on columns first, mainly because they're simple and there are a lot of fragility curves that are available for that, and we can do the modeling relatively quickly. And you can see there's almost all the bridges, like 90%, are circular bridges, and there's a bunch of assortment of other things which occur mainly for architectural purposes. The year constructed is obviously an important feature, and not surprisingly, 70% of the bridges were built between 65 and 70, or so 60 and 70, 55 and 70, because that's when the interstate system was built. So having that big old loop, the big old center is not surprising. Unfortunately, it kind of straddles, it's right around the 1971 San Fernando earthquake when all the codes start to change. And something to understand is that codes change differently in different parts of the country. They changed in California the fastest. They had the earthquake, they're more attuned to earthquake damage. And then it spread throughout the country, and then some bridges had already been designed, and some bridges had not been designed yet, and so the rules were put in, but only put in on new bridges. So you'll see the provisions and the seismic vulnerability of the bridges isn't just stopping at 71 or even at 74 or 75. It's actually a process that has a lot of variability in it. Of course, we can characterize all the properties. And our initial plan had been not necessarily to try to use machine learning to get the answer. The initial plan had been to characterize distribution. So then we have a bridge where we know we have a bridge, a certain type. You could imagine rather than guessing the column size or guessing the reinforcement ratio, you can imagine trying all the probabilities based on this distribution, assuming that the bridges we looked at are representative of the larger inventory. So in this case, you can see, it's interesting, there's the column reinforcement ratio, which is actually down here. You can't see the label on the slide. We know a lot of columns are governed by the 1% minimum reinforcement ratio. What's interesting is that there's actually a decent number of bridges which are below that, just because who knows what happened during the design process. So one option would be to take all these distributions, take the correlations between the properties, and you could go through and just do a Monte Carlo process and then do a bunch of detailed analyses to replace the hazardous one, which basically lumps all these things together. And that way you would take into account the properties of your inventory. One of the key ones, which doesn't really take machine learning to look at, is the spacing of transverse reinforcement. You can see spacing on the vertical axis and then the year built. And if I superpose on top of that the 1975 San Fernando earthquake, you can see that before then, with the exception of 3 or 4 bridges, it's always 12 inches. That's because until the San Fernando earthquake hit, transverse reinforcement was there to hold bars in place during casting. So all they cared about, it could be number 3 bar or number 4 bar, but all they cared about was when you put the concrete in there, those bars would stay in place. And what's interesting, if you can see that region, but then between, say, 75 and 80, you can see there's still a bunch of bridges that are still being constructed with 12 inches. I'm assuming those were designed before the codes were changed. So you actually have a period of transition where you have great uncertainty. And as you move to the right, then you can see the spacing gets smaller and smaller and smaller as the modern provisions come in. Okay, and so here's an overview of the machine learning process. I talked about some of the details that I found were super interesting. The amount of time spent on the encoding and trying to figure out how to describe the data was huge. You do things in categories, you do things in range. It's not just a function of what the data looks like, but it's also a function of what you want to do with the data. Do you care, say, number of columns? Well, if it's a single column bent, that's going to be in single bending. If it has 2 columns, it's going to have 2. If it has 3, it's going to have double bending and 4. So in that case, you actually don't care about the number of columns, you just care about whether it's 1 or something else. And so I'd say the majority of our time has been playing around with the encoding process of trying to figure out how do I represent that data so it describes what I'm seeing, but also is telling me what's relevant to the outcome. And then the other thing I found interesting as well is that we have a small database. We only have about 350 columns that actually have, reinforced concrete columns for which we have all that information. And so what we ended up doing was essentially to run the algorithm. We want at least 100, to have a training set and then apply it to a different set. Well, when we have 300 or 400 to begin with, it turns out that selecting your training set can change the results an enormous amount, even if you're changing your training set in a random way. So by the time we were done, we found the best way to get consistent results so that every time you do run your analysis, you get the same number, is to basically do it 10 times. So every single learning process was done 10 times, where you essentially pick 100 bridges side by side, you do your training, then you apply it to the 100 bridges, you get your stats for that, then you mix it again, and you do it over and over and over again. And then all your stats you're going to get are actually going to be, for example, you're going to have an R squared, or whatever measure you want to use, but it's going to have uncertainty, because in some cases, the machine learning model worked really well, at other times, it didn't work so well. So you actually have an uncertainty in how good your model is going to be, based on the fact that your set is relatively small. Okay, so this is a slide where my machine learning colleagues have spent a half hour chatting about it. They went through and applied actually 6 different or 5+ different algorithms. You're familiar with decision trees, random forest, and things like that, XBoost and whatever. But then what I learned, which you guys maybe know already, is of course it changes how good things are going to depend on what you're trying to predict. That's not surprising. And on top of that, what I did not know about until I did this project is that if you run the AutoML kind of type of program, or in our case we use AutoGluon, it basically tries to take advantage of all the others, and then the ones that work the best it uses. And it takes kind of a weighted ensemble to get the results for that. And it's not always the best, but it's always the best or almost the best. And so despite having done all that work, and by the way, we can do this because we're talking about relatively small data sets, right? So using 10 different algorithms might not make sense if you have 1 billion points, but if you're making something and you have hundreds of outcomes, it's really not a big issue. And you can see it depends what you're trying to predict. Longitudinal reinforcement ratio, R squared is not exactly what we want to know, but we're way down at 0.15, whereas transverse reinforcement ratio is 0.77. And if you look at the next plot, we'll look at why that's true. It's not too surprising. So, yeah, it depends on what you're trying to predict. But AutoGluon was, again, always the best or almost always the best. And AutoGluon is just one type of AutoML. And then what's, I think, probably more interesting from the machine learning is you start looking at the kinds of weights. And I'm not going to go through the details of that. I enjoyed the discussions. You can imagine different things that are more categorical. One algorithm is going to work more than the other. If it's more big changes in magnitude and you want to care about the magnitude, other algorithms work better. And if you look really closely at all the algorithms and the 10 different properties we were trying to predict, then you can see there is actually predictions. You can say that, oh, it's better to use a neural network for this or use XBoost for something else. What's nice about AutoML is that it just kind of figures it out for you. So if you have the computational power, it's really easy for a non-initiated person to not have to pick through all these algorithms and just use the black box, which then you can see uses tons of different, all the algorithms. And if you look at the details, if you can't because it's too small, it turns out that columns per bed and longitudinal reinforcement ratio, this is more kind of categorical. On the longitudinal reinforcement ratio, it's a different range. It turns out that different algorithms contribute more to the solution for some parameters, but not other parameters. And so AutoML is kind of nice because it basically does that for you. As an engineer, of course, what I care a whole lot about is a feature importance. So it gives you some insight. So again, I have columns per bent, column minimum aspect ratio, longitudinal reinforcement ratio, and transverse reinforcement ratio. You can see on the lower right, year built is going to tell you transverse reinforcement ratio. Other stuff is basically noise. And we thought we'd spend some time like removing things, like I'm not sure why the operating rating would affect the result. Well, turns out taking it out makes almost no difference at all. So we spent a lot of time cleaning data and redoing data and trying to make it better. Yeah, it turns out that the first shot with AutoML pretty much got what we needed. So let me go to the next step. So we said, let's see how far we can go and try to actually solve a practical problem. I developed this little thing called a shear failure index. It's not super important. What it does is it basically tries to predict the likelihood that you can have a shear failure versus a flexure failure of a column. And it has transverse reinforcement ratio, the aspect ratio, longitudinal reinforcement ratio, and then a factor which depends on whether you're in single curvature or double curvature. And if you look at that ratio, again, the details don't matter so much for this talk. If you look at the database of different failures, you can see that ratio is now at 0.4. It's all blue, which is essentially a flexural failure, shear failure. If it's all the way at larger than 3, it's all flexure failures. And in between, you go from shear to flexure shear to flexure. And essentially, this model is one quick way to screen bridges and figure out whether they're susceptible to shear failure without having to do the displacement ductility demand, which is, of course, a lot of work. So what we did then was to train the algorithm to compute this ratio. And it's really challenging because it's the function of a bunch of other things: aspect ratio, reinforcement ratio, longitudinally, and transverse. And you can see if I look through 100 columns and I were to look at things randomly, you can see that the red line is, of course, what you would get. You'd be picking up columns randomly on a straight slope. If you had perfect knowledge, you'd be at the blue line, which means every single one you pick up, you already know is shear failure. And then don't worry about the yellow and green, but that's essentially what you get the first one. So you can get the first 20% of the bridges by looking at 9%. So if you're looking at just making sure you want to do that. That's acceleration of a factor of 2 or so. As you get longer there, then it gets less good at picking up those later bridges. So now you're saying, gee, if I do it randomly, I have to look at 8% of the bridges. I run your algorithm, and I still got to look at 60% of the bridges. It's an improvement. Radical? I wouldn't think so. So the next thing we said was, well, what would we need to do to make this thing work? Well, one option would be to take some of these parameters as features as opposed to targets. And so in our assumption, we decided that we already got all the street view information out there, and we got the column aspect ratio as a single feature. If you take that as a feature rather than a target and run through the algorithm, you can see the difference between before and after, and now you're talking about a better performance. So you have a factor of 2 at the later versions. In the beginning, you have a factor of 3. So whether you want to use this or not, I think we need to keep on working on making the algorithm better, figure out how to get other data to supplement this. But it was certainly a fun journey, which I've enjoyed. So just to finish up, so I'm over time. AutoGluon worked, or AutoML worked best in general. You really have to sample a bunch of times for small sets. I found it mainly helpful for the machine learning, like to be able to identify the best algorithms. I liked it for pre-processing and also try to figure out what the feature importance is. And then when we pushed it to say, can I actually predict shear failure, it was really good at getting columns at first. And the more and more you try to get that last shear failure, the harder and harder that it is. And that's not uncommon because there's some of these which are right on the edge. So of course, in the end, we're saying maybe what we need to do is take this information, combine it with Street View, and then we're off to the races. Thank you.